In this lesson, we are going to practice running both of the classical techniques we discussed, the Viola-Jones algorithm and the HOG algorithm. For this exercise, we will load a Jupyter notebook and play with the code there. We'll use the OpenCV library in this lab to see the Viola-Jones object detector and the HOG plus SVM detector recognizing objects in images. Specifically, faces and eyes for Viola-Jones and people/pedestrians in the case of HOG plus SVM. Both of these systems rely upon handcrafted feature extractors. In the first part of this lab, we'll use Viola-Jones to detect where in this image the three faces are, and draw red boxes around them. Then, using those face detections, we'll try to find where the eyes within them are, and draw green boxes around those. You'll notice a few false detections, or false positives, where it is obvious to you that there isn't a face, but the shading patterns in the image are such that they fool our Viola-Jones detector. You'll also notice a few missed detections, or false negatives, where it missed an object. This is particularly the case with the eyes. Feel free to play with the parameters of the detect multi-scale method to change the scale stride and change the minimum number of neighbors. You can then rerun the notebook starting from where we call cv2.imread to load our image again and to plot new detections. In the second part of this lab, we'll use the histogram of oriented gradients feature extractor with a support vector machine classifier to detect people. HOG plus SVM was hugely popular until about 2012, when CNNs came of vogue. We'll again use the OpenCV implementation of HOG to show it in action. We'll create a detector for people and then look for detections in our image. Notice in OpenCV's HOG we have to specify our window stride, padding, how many pixels either side of our image we want to fake, and a scale factor. Try changing the win stride parameter from 4,4 to 8,8 and see what effect this has on the number of times the person is detected. Now try changing it to 1,1 and notice how much longer it takes to run. We're now striding our sliding window detector by 1 pixel horizontally at a time and 1 pixel vertically when we reach the end of a row. Look how many overlapping detections we get now. We'll finally use a routine from the imutils library to implement non-maximal suppression. That is, to group all the overlapping bounding boxes together into a smaller number of boxes.